thank you so much for everybody who registered and everybody who is attending the latest in our series of HexAuFoil related webinars. I'm absolutely delighted today to be welcoming two speakers from the Asbury Centre at the University of Leeds, Yehuda Halfon, who is their cryo-EM manager and a postdoc at the facility, and Sebastian Porav, who's a researcher in the Robin Bond group on FRITC 145. We're going to have two parts to this webinar. Yehuda is going to give an initial introduction to their experiences with collecting with HexAuFoil and with Quantifoil grids more generally at the Leeds facility, with some hints and tips on how to optimize the data collection for efficiency, maximum efficiency. And then Sebastian is going to talk in detail about one of the structures that he has solved with HexAuFoil recently, and how that compares to when he collected the data on ultrafoil. So I think it's going to be a really exciting couple of talks. We won't have any questions until the end of the talks. You can see on your top right a button to click to ask questions in text. We will address all the questions at the end of so please just put your questions in as you think about it for the speakers, and we'll come back at the end and answer those questions. If we don't have time to get to all the questions, we will then send out an email addressing any open ones after the end of this seminar. So thank you very much. And with that, I think we'll start and hand over to Yehuda for the first talk.
My name is Yehuda Halfon, and I'm a cryo-EM scientist in the University of Leeds. I'm honored to be hosted today by Quantifoil to give a talk with my good friend and collaborator, Sebastian Porav. Our talk will be split in two parts. The main title is HexAuFoil Ultra Small Hole Gold Grids from First Image to Final Structure. I will give my part of the talk about sample preparation, grid screening, and data collection. But before we even go how to do sample preparation and screening and all that stuff, there are some things we in our facility recommend other users in other facilities to make sure their facilities do have it, to make sure it will work properly, collect data properly, and your life will be easier, because HexAuFoils are not your normal grids. They require a bit more handling and a bit more setting up. Our setup is we have two Cryos G2Is. They're a bit old, but they can still do everything any other Cryos can do. We have a Selectris, and one of them, which is the Thermo Fisher Energy Filter, and both of them have Falcon 4Is, which enables us to collect very high speed movies and very fast. The first thing you want to make sure is that your facility have fringe free. Fringe free means that you can narrow the illuminated area almost to the size of your detector. That means that when you work on a very small hole, like in HexAuFoils, your beam will be almost the size of your hole. So you don't get illuminated area on other holes, so you don't burn your samples while you're collecting one hole, you're actually burning a different hole, so you're losing data. Fringe free is very important in this. You can get around with it. You'll get less holes you can collect on, but it's very important to have it. And another important thing is to have aberration-free image shift. Aberration-free image shift lets you collect faster data by moving the stage very occasionally. It just moves the stage every time it finishes a cluster of data. It collects the cluster by moving the beam around. The default diameter of AFIS is about 10 microns. This is sometimes changing based on your EPU version. The engineers in Thermo Fisher do change it without letting the people know that they change it. But in the last few years, it has been 10 microns. If you do have other preferences, talk to your facility managers. They can change the settings inside EPU program to make sure that you get the proper settings you want. If you see that you don't get the proper images at the 10 microns, maybe you want your AFIS range to be 8, and then it will be more accurate. Now let's start talking about grid preparation. The first thing we need to do when you use a grid, any grid, is glow discharge it. We have two main devices in our facility. One of them is the Pellico Easy Glow, as you can see here on the right side. It has advantages and disadvantages. One of them is that it uses air as the gas by default. So if you have sample that is sensitive to carbon or other gases in the air, it will be harder to use it. You will have to connect to the pump different gases and run it through it, and then you have to vent it, and it takes longer. And it only glow discharge your grid on one side. You put your grids here in this area, and they're facing up, so they glow discharge from one side. So you might want to flip them after you glow discharge them and glow discharge them again to make sure it's properly charged, because these grids are pure metal. You need to glow discharge them more than just normal carbon like Quantifoil grids. But it's very easy to use. You set up your parameters here on this screen, a few buttons, and then you click one button to start, and you can come back after 5 minutes, and it's done. In HexAuFoil grids, we do recommend using 1 minute at 30 milliamps, and then flip the grids and do 30 seconds at 30 milliamps again. This will make sure that your grid is properly charged and you don't get blotches of ice on your grid. Another kit we have in our facility is the amazingly named Pi Scientific Tergeo EM. This is a plasma cleaner, and it's not a glow discharger. So what does it mean? It creates here, there is a chamber that you cannot see, creates the plasma here, and then there is a little hole that transfers the plasma over your grids that sits on a little table, and glow discharge them and clean them very gently. The main advantage of it, it's set up to use different gases. In our facility, it's connected to oxygen, nitrogen, and argon, and not CO2. So that means that your sample is always carbon-free. We have some users that carbon activates the protein and they don't want to do it, so they use Tergeo to get better results. It, like I said before, it plasma clean on both sides of the grid in one go, and it does it more gently because it's just a flow of charged plasma and not a lightning storm like in other machines. It is more complicated to use. It's not like you set up your parameters, press a button, go away, and come back. You have to vent it manually, you have to pump it manually, you have to set up your recipe, make sure it works, and then you click start. It's more of a hassle, but it does the job differently. So if you want to use a plasma cleaner, go for it. It takes longer, but the results are very good. Now about blotting the sample. In our facility, we have the VitroBot Mark IV and the Leica EMGP1. For single particles, we use the VitroBot. It's easy to use and most people know how to use it. It's hard to talk about blotting conditions because they are vary between everything. If your sample is gloopy, you want longer blot time. Maybe you want blot twice. If your sample is very prone to evaporate, you maybe want to use less wait time or none at all, just apply and blot. If you're using different kinds of paper, like ash-free paper or things like that, this will change your blotting conditions. Also, most of the conditions in your VitroBot depends on how the engineer calibrated it. So if they calibrated the blot force to a slightly different parameter, your blot force and blot time will not be the same as other VitroBots. So it's hard to recommend what to do. In our facility, we use a 10-second blot time, blot force of 6. This gives us most of the time very good results. Again, with, I'm air quoting here, generic samples. If you have more gloopy sample, blot more. Otherwise, you will get very thick ice and you might not get anything. Now, after we made our grids, your facility or you put up your grid inside a microscope and you think you are ready to start screening the grid. In our facility, the first thing we always tell the users to do, no matter if it's HexAuFoils, normal grids, tomography, do image shift calibration. In general, we always recommend students to treat the screening session as a data collection session. So if you make everything aligned and properly set up initially, you don't have to spend time at the end of the day to do it. Usually in the end of the day, everybody wants to go home, nobody have time to do things properly. So spend a few minutes at the beginning of the day, do these things. For image shift calibration for HexAuFoil, it's a bit different than normal grids. In normal grids, you don't have to be super accurate. If you're up to half a hole away between data acquisition and heliocentric, it's not that bad. The beam can move there, it's fine. As long as EPU finds the hole, everything will work fine, it's okay. In HexAuFoil, on the other hand, your hole is so small, you have 300 nanometer holes, you have to be very, very accurate. If you're not, you'll collect a lot of gold and not holes. We recommend, as before, as normal, start with a big chunk of feature. So if you have ice that you can see in Atlas magnification and in all other magnification, use that, go to eccentric height, make sure you see that feature, align everything towards it, do the image shift calibration, and this is a good starting point. Why is it a starting point? Because after you've done it, we highly recommend do it again, but this time in the middle of a hole. You want to make sure everything is aligned to a hole, to the center of a hole that you are in. If you can do it in the center of the hole, in the center of the hexagon, that will be even better. Don't go to the edges. The edges are harder to find. The center is the best way to do it and the most accurate way that we could find it. And after you've done it, move to a different hexagon, go to eccentric height, and test if you are in the right place. If not, do it again. It's better to spend 10 to 15 minutes doing it over and over again than to start your collection realizing that you're off by a hole or two, you're collecting a lot of gold, and just stop, do it again, and then you have to maybe you have to redo the EPU session again, and then just work well at the beginning and it will work well for the rest of the day. And about the settings for the grid screening, so we start from the Atlas magnification, the Atlas preset. We recommend go as low as you can go, that you can see enough hexagons that you get good stitching, but you don't want to go very low because sometimes you start to see the C2 aperture, and then all your images will have like a little bit of half moon in your image, and you don't want that. On the right, you can see a HexAuFoil grid that one of our users made, and you can see the gradient because we used the Vitrobot. So you see thick ice here, thinner ice here. You see a lot of broken grid squares, grid hexagons, and it's okay because we are all human. We are making grids, we break squares, we break hexagons. It's gold, so it's more fragile than Quantifoil. It happens. If you're used to it from normal grid, you're sometimes like, oh, I broke a lot of squares, this is annoying. In this case, always remember, in each hexagon you have 5,000 holes. If you find a good hexagon, it's fine. You need like 3 or 4 to get good data set. So if you have all this area of thick ice and broken hexagons, it's still fine because this area is very good, and these 4 could be all you need to collect good data. In the grid square magnification, what we want to do is see one hexagon. I know it's sometimes hard because it depends on the orientation of the grid inside the microscope, and you cannot move the grid fractions of degrees to get it properly. Try to get one hexagon per image. If you start to see more holes on the other sides of your image, EPU might find them when you make your session and try to think they are the same holes as your hexagon, and will try to go there to collect data, and then it will collect the data twice. So if it happens, make sure that in EPU you delete these areas that you don't want to collect on your hexagon, because again, we don't want to double collect things. Heliocentric, is something of different than normal grids that we usually do. In normal grids, we usually recommend the users to have one hole in this image. You don't want to get multiple holes in an image. It will confuse everything. It will be hard to find the holes in EPU session. But in HexAuFoils, we found out it actually helps it to get to proper eccentric height and more accurate. Because it has more holes to compare to, it's usually easier for it to do the cross correlation better and get to proper eccentric height. And also we found out that EPU is getting smarter, so if it sees more holes in hole eccentric, it doesn't get confused anymore. So it's good for everyone. Data acquisition. We recommend going on the highest magnification you can that your EPU is calibrated for, otherwise it will get wrong data parameters. To make sure, if you don't know how to do it, go to the highest magnification you can on your EPU, click preview, and if you don't see pixel size or exposure dose and things like that, go a lower mag until you do it. It doesn't mean your microscope is not calibrated to it. It means that the engineers didn't calibrate EPU to it. So if you really want to collect in this magnification, just call Thermo Fisher and tell them, I need to calibrate to my highest magnification because I want to collect very, very, very high magnification. And they will come, they will do it. It takes a few hours and it's not very complicated, but they need to do it. You can't do it yourself, sadly. And as you can see on the right, I do have some gold in it. It doesn't really matter. I chose this picture in particular because you do see some gold in it. Otherwise, it will be just a gray picture. So it's boring. And in this case, the pixel size of the image is 0.53 angstrom. In this microscope, we can get to 0.41 angstrom pixel size. And it's slightly better, but I didn't see much of a reason to put that picture because it's even harder to find gold in it to show you. Yeah, it's an actual hole and not just a gray image. So like I said before, you do see some gold. I remember in the old days when ultrafoil grids came out and other gold grids came out, a lot of people were, oh, I don't like gold grids because you have to collect only in the center, because if you see gold in your image, it will ruin your data processing because of the gradient. You cannot see the particles. It's okay that you cannot see the particles. The software can. And if you have big enough particle with a big enough contrast, you still can see it even when you have gold in the image. Seb will talk about it later in his talk. And he will show you how it doesn't really affect data processing and particle picking if you do see gold in your image. So don't be afraid that you have small holes that most likely will get some gold in it. In EPU, you can chain all the high magnifications to the data acquisitions. Most of the time, you can do it. Most of the time, it works well. Sometimes the tone ring magnification and the drift doesn't work very well, so you might want to make them slightly lower magnification. This helps them with the cross correlation. Tone rings, to be fair, it doesn't really matter. You only use it for alignment and you don't do it on gold anyway. And drift, there are a lot of people that don't use drift correction anymore. So if you don't use drift correction, just ignore it. If you do use drift correction like we do, sometimes you do want to make it slightly bigger, lower magnification, so the cross correlation will be better. Otherwise, you will end up in an endless drift loop even though nothing moves. And now, after we set up everything, we can actually screen the grid. So how do we screen the grids? It's fairly simple. It's very similar to other grids, but with a few caveats that we recommend in our facility. For the first hexagon in your grid, I recommend go to eccentric height manually or as close as possible manually. This will help you get faster and more accurate autoeccentric after you do it. There is a problem with autoeccentric in grid square and eccentric magnification, that if you are in grid square, you have too many holes it's hard for him to do proper cross correlation. And in heliocentric magnification, if you're too far away, it just sees holes and it's like, they're cross correlated, it's fine, I can do it. But if you can do it manually, it's sometimes hard, sometimes annoying. You need to use VLOX or the flu screen. If you're not using energy filter, you can use the flu screen. If you are using an energy filter, you need to use VLOX. It's slightly more annoying, but if you can do it manually, it will get there faster when you do it automatically. And I highly recommend to do it for the first one, because this is the biggest difference between zero of the stage to the proper Z height of the hexagon where it should be. And like I said, in autocentric and grid square magnification, it fails because it has a lot of holes, and the magnification is basically all you see is two hexagons which are black and 5,000 tiny white holes. The cross correlation just gets weird and it gets confused. Best case scenario, it fails and it tells you I failed. Worst case scenario, it gets the wrong Z height and you think you're in the right Z height and then it fails. And then you have to do it manually anyway. And if you're too far away from eucentric, the auto-eucentric and eucentric height preset will not be accurate, because it will just think, oh, I see a few holes, they're fine, it's good enough. And I want to show you how can you tell very fast if you're in eucentric height or not. So in this case, in this image, it looks fine. You see holes, they look nice. But if you look closely, you could see in each of the inside of the holes, you will see like rings. This means you're not in eucentric height. It means you're not very far away from eucentric height, but you're still not in eucentric height. And if you are in eucentric height, you can see it looks flat. And this means you are closer to eucentric height, it's better. And you can see there is also slight difference in the gold color in it. I'm not sure why there is a slight difference in the gold, but the closer you are to eucentric height, the gold is slightly brighter. And if you go, the next thing you want to do is you go in a higher magnification, you take an image. You don't have to correct for autofocus, just take an image in high magnification. And if you don't see rings inside the holes, you're in eucentric height. And this is very important. And why is it important to be in eucentric height, you ask? So when you are in eucentric height, when you collect the data, it's more relevant when you're making the EPU session and actually collect the data. Because if you're just screening, the autofocus can correct for some difference in the Z height. But if you are doing an EPU session with AFIS, it might get completely wrong. So if the grid plane and the eucentric height are the same height, the beam goes down to the center hole, and then it collects it properly, because we all know it's just perpendicular to the beam. It hits it, it works fine. And then when it goes to up to 10 microns in the AFIS range, it still hits the center of the hole and everything is fine and we're all happy. But if you're not in eucentric height, the grid plane is here, or the eucentric height is here. It could also be vice versa. The grid plane could be above the eucentric height. And then you see it's still basic geometry. The hole in the center is still fine because it's still perpendicular, but EPU thinks, oh, I'm at this height, so I have to apply this angle to get to 10 microns. So it applies the same angle. It is the same angle between the two triangles. But you can see it hits here, which you don't have a hole, because the hole is still here. It's still 10 microns away from the original hole, and it misses the hole. And this is how you collect more and more gold and less holes. This is why it's very important to be in eucentric height. If you are in eucentric height, if everything is, you did everything correctly and everything works fine, and you still see a lot of gold, maybe your AFIS is not very well calibrated, talk to your facility managers. Usually they know how to calibrate for the AFIS. It's not very complicated. It just takes a while to do it. And if it's more robust than what we in the facility can do, we need to do it. We need to call an engineer to do it. So make sure that everything is correct before you collect your data. And let's go back to screening. The best thing in my part for HexAuFoil is the ice is very uniform in the hexagon. So unlike in normal square grids, when you have big holes and small, not very big squares, you have a gradient inside your square. So you have to make sure how the center looks, how the side looks, how the middle looks, and all that stuff. And then you find the proper ice and you collect there. In HexAuFoils, the ice is very, very uniform. So it's enough to take an image in the middle of the hexagon and in the side of the hexagon to make sure that you still have nice particle distribution. If you really want to make sure, screen one more hole or two more holes and you're done. You can move on to the next HexAuFoil. It's that easy. And then once you find good hexagon, save it. You love it. It's good. And remember, there are about 5,000 holes in a hexagon. I'm saying about because it depends on the ice thickness. If your particle is like thicker ice, so you will have less holes, but you'll still have in the thousands. I think the smallest number of movies per hexagon that I saw was over 2,000 movies per hexagon. And this is a very high number of movies. Once you have enough hexagons, I just recommend go to data collection. Again, it takes a long time to set it up. You want to run it with your facility for a while to make sure everything works well. And since you need 10,000 to 12,000 movies in a decent data collection, and you collect about 1,000 movies an hour, on our setup, I think K3 can go higher than that. You get to, in 10 to 12 hours, you're done. So it's a very fast collection, and you only need like 3 or 4 grid squares, hexagons, so you don't need a lot. And now we'll move to the data collection. A thing we recommend highly is to align the microscope before you do the screening or just before you're setting up your EPU session. Don't set up your EPU session, swap the grid to the carbon grid, align the microscope, swap back to your HexAuFoil grid and start your session. You will lose accuracy. And after you've done your alignment, re-atlas the grid you want to look at. It helps. If you take it in and out, it helps. Accuracy is key. Even though EPU has a correction of movement, it's still, because the holes are so small and everything is so need to be accurate, slight movements will be the difference if you collect 10,000 good movies or about 6,000 good movies and 4,000 gold movies. Make sure you're using APHIS. If you cannot use APHIS, if your facility is not set up for APHIS, but you really have to use these grids because your very small flexible protein is the only protein that really loves this type of grids, use it. Just be aware that you will collect very slowly, about 200 movies an hour, because it moves the stage every time and it takes longer to do stuff. So highly recommend using APHIS. Select the hexagon you want to collect from and then go to eccentric height. Again, I recommend, like we did with the screening, make sure you're in eccentric height. Don't trust EPU that it says I'm in eccentric height. Take a few pictures to see that you are in proper eccentric height. You don't see the waves in the holes. Everything will be better. The more accurate you are now, the less you need to fix later. So it's always good to do these things. Make sure the center of the hexagon is the middle of the image when you require the image in EPU. If it's not, do it again and again until it is, because if EPU thinks, the thing is, EPU thinks this is the center of the hexagon or the square, and it doesn't matter what type of grid you're using. In our case, we use HexAuFoil, so it thinks this is the center of the hexagon. And this will be a problem because it applies the APHIS, so it will think you collect in one way and it actually thinks in a different place, and this will lead to, again, black images of gold, which you don't want, or even worse, black images of the grid bars, which you definitely don't want. So make sure this is happening. Another way to make sure this is happening in EPU, in the latest versions, I don't remember when they started it, I think it's 3.5 or something. There is an option to choose hexagon. And if you go to gold grids, you can choose hexagon, and it helps EPU understand, I'm actually looking on the hexagon and not in the square, so things may be slightly different. Use it, it helps. If your EPU version doesn't have it, ask your facility people, can you please update EPU? It helps, it saves some time, and it saves some frustration. When you do the measure hole size in the settings, make sure that the yellow circles, which is very annoying to do yellow circle on black grid, the contrast is annoying, you can barely see it, but zoom in and make sure that the yellow circle is in the middle of the hole as accurate as possible. Try not to get any gold, it will help you. The more accurate you do these things, the more accurate things will be. And again, try to find the nearest hole to put the other yellow circle in. Make sure both sides are the same. We know that not all holes are identical, so go for the smaller one. If you have two holes near each other and one of them is slightly smaller than the first one, you go for the smaller one. It's better to err on the side of small than to err on the side of big, and then you get worse images. And then you just continue as normal. You add up your the focus range, where you want to do the autofocus, when do you want to do the autofocus, drift measurement, yes, no, all these things, and do it for the rest of the grid squares, the hexagons, and once it's done, everyone is happy. I will give you some tips and tricks that we learned over the year and a few months that we are doing hexagons in our facility. Align the microscope before anything else. Set up your session. You usually know what magnifications you want to use. Your facility should have beginners presets you want to use for hexagons. And to be fair, when you align the microscope, all you really care about is the highest magnification, and the facility or you should know what is the highest magnification you want to collect on. So put in the carbon grid, align the microscope. This will make your life way easier because you don't have to load the grid back and forth all the time. If your first grid is good, just collect on it. Once you find the grid you like and you already aligned the microscope and you said, okay, this is the grid I want to collect on, go to each center of hexagon you want to collect on, and the TUI, the TEM user interface, go to the search tab and click save location. This will save the X, Y, and Z of that location. You already know you're in good heliocentric height, you know you are in the center of the hexagon, and then when you set up your EPU session, instead of moving the stage everywhere, you just go to the locations you know you are, and then you click go to, and it will go to the proper X and Y, Z location. Then you just click acquire, and EPU will remember this is the X, Y, and Z location as the right location you want to be in. This will make everything way more fast and way more accurate, and we all want fast and accurate data collection. The faster you set up your collection, the more movies you can collect, and the more accurate you set up your collection, you can actually collect instead of just sitting there trying to fix and go back and forth with settings. Plan your day ahead. This is something I keep saying to my users. It's longer to screen HexAuFoils. It's not as easy. It's not as straightforward. When you have HexAuFoil grids and you want to screen them, book a day to screen the HexAuFoil grids. Not, I have 3 Quantifoil, 2 golds, 1 HexAuFoil. I want to change parameters. This will make everything way, way longer, especially if you want to collect on the HexAuFoil. If you just say, oh, I want to see 3 images on the HexAuFoil, but I don't want to collect on it. I want to collect on a different day on a different microscope because I got a different setup somewhere that I want to collect on this. Fine, it's okay. You can do this. But if you want to collect on the HexAuFoil, just load HexAuFoils on the microscope with a grid you can align on, and that's it. Don't mix and match, plan your day. Don't atlas the grids go disappear because you have some lab things to do, you have some meetings to attend, and then you come back at 3 p.m. and okay, I'm ready to set up things, and then nothing is accurate, nothing is working. Some facilities will not be there to help you because some facilities leave at a certain hour. Some facilities will stay, but will not be happy about it. So plan your day ahead. You say, I have a HexAuFoil day, I'm in the microscope, full stop. And if you will follow all these tips and tricks and all the things I talked to you about, you will win. You will get things, everything will be awesome. And I wish you good luck with HexAuFoils. They are an interesting grid to work on. They're not easy, but the results are very good. Thank you all for listening. I've been Yehuda Halfon from the University of Leeds Asbury Biostructure Laboratory, cryo-EM facility. And thank you for joining us, and hope you had fun and learned some things.
Thank you, Yehuda, for that really interesting view into your recommended methods for collecting data with HexAuFoil and indeed with grids more generally. It was a really interesting view into how facilities, how we can help facilities collect the best possible data for our projects. And now I'm really excited to move on to Sebastian Porav, who will talk in detail about one particular example of using HexAuFoils to collect data and comparing that with ultrafoils. Sebastian is a researcher also at the Asbury Centre.
Hello everyone, thank you for joining us today, and thank you Claire for giving us the opportunity to share our experience with the HexAuFoil grid. I'm Sebastian Porav, a research fellow at the University of Leeds. I'm working in Dr. Robin Bond group, and my work revolves around TRPC145 structural biology. An overview of today's presentation. In the first part, I will give you a short background on TRPC145 biology and their organization, followed by HexAuFoil data collection and data processing, with a focus on early stages, especially particle picking and 2D classification. TRPCs are part of trip-ion channel superfamily, which is better known for capsaicin receptor TRPV1 and mentor receptor TRPM8. Compared with the ones that I mentioned, TRPC145 don't have a specific function. They rather work as integrators, silencing or amplifying signals. They are implicated in numerous functions across the body, and when they don't work properly, we start to develop numerous pathologies. Our group is focused on the involvement of TRPC145 in the pathology of the cardiovascular system. TRPC145 are ligand-gated cation-permeable channels characterized by 6 transmembrane domain with both termini located intracellular. In the N-terminal domain, we can find a few ankyrin motifs, while the C-terminal domain is dominated by the presence of an IDR. Between the 3 types, there is a high similarity but also significant differences, especially at the C-terminal level. To form a functional channel, they need to assemble in tetramers, which can be homo or heterotetramers. In order to actually understand how these channels work, we are frequently solving TRPC structures in the presence of different agonists and antagonists, both natural and chemical synthesized. I think that's enough for background, so let's actually look at the data. I think this was the first HexAuFoil grid that we used, so we didn't do any optimizations in terms of protein concentration, additives, or grid making. For grid vitrification, we used a Vitrobot and mostly followed the recommendations from Quantifoil. So compared with normal grids, we doubled the blotting time from 5 to 10 seconds, and we increased the blotting force from 1 to 6. We glow discharge them in a Pelco Easy Glow with the normal settings for 2 times, once for 120 seconds, followed by an additional round for 30 seconds. These are the normal settings that we are using with with the normal gold ultrafoil. As you can see, we got a very nice ice gradient, and all the holes in a hexagon had very uniform ice. In the right image, you can see the aphis grouping of one of the hexagons that we actually collected the data. Because this was the first time that we used the HexAuFoil grids, we wanted to compare them with the normal gold ultrafoil. So we also made an ultrafoil grid with the same batch of protein. In both cases, we collected around 12,000 micrographs, which took roughly 15 hours. In case of HexAuFoil, we had a pixel size of 0.49, while for UltraFoil was 0.74. We had around 9 particles per micrograph in case of HexAuFoil and 35 for UltraFoil. In both cases, we got very nice maps with a resolution of 2.5 for normal UltraFoil, while with HexAuFoil the resolution was slightly better, 2.4 with particle binned 2 times, and 2.3 with unbinned particle. There is a big difference in terms of computational time for refinement when you are using unbinned particles, but the resolution, it wasn't the difference in resolution wasn't as big. In terms of data processing, we did everything in CryoSpark. As I mentioned, we roughly collected 12,000 micrographs in both cases, which we motion corrected and CTF estimated in CryoSpark. And the entire workflow is pretty much basic, involving block picking, 2D classification, selection of 2D templates, template picking, 2D classification again, generating 3D models, and running heterogeneous refinement. What's probably different from a normal processing workflow is that we are using the following steps. We are using the full particle stack that we obtain after template picking to run several heterogeneous refinement jobs with one good class and a few bad classes. And after that, we are using a 2D classification on the good class to remove the rest of bad particles. Using this approach, we usually recover more views of our protein. After the 2D classification, we are using non-uniform refinement or homogeneous refinement. It's case dependent, but in this case we use non-uniform refinement. As I mentioned, we wanted to compare the UltraFoil with the HexAuFoil grades. So first we looked at the micrograph quality. And when we looked at the average defocus and the CTF fitting, we noticed that the HexAuFoil grades provided more uniform data, as you can see in the 2 images. In terms of picking, I will only show you the HexAuFoil. You can see some micrographs with different defocuses and their corresponding picks after a block picking job. We found it very easy to adjust the picking threshold to remove the picks on the gold. And also we found very interesting that we didn't have any picks close to the hole edge. At the bottom of the slide, you can see that the picking worked beautifully. We got a very nice 2D classes that we used as templates for a template picking job. Here you can see the same micrographs, but this time with template picking. We had the same observation, easy to remove picks on the gold, and we don't have picks close to the edge of the holes. And these are the first round of 2D classification that we did on the template picking. So to compare the 2D classes from HexAuFoil and UltraFoil, we didn't compare them after template picking. We only compared them after the last 2D classification, after the heterogeneous refinement that I was mentioning previously. When we looked at the 2D classes obtained from both type of grades, we couldn't see major differences. In both cases, we got very nice 2D classes. And what you can see with red diamonds are the classes that we are usually recovering using this approach. These are normally very low populated, and we found them to be crucial to get very nice maps with good resolution, usually below 2.7. Further, we compared the 2 maps obtained from the 2 datasets, and as you can see in both cases, the maps looked very good, with nice density for the side chains. You can see the high quality of the data by how well the transmembrane domain is solved. When we compared the two maps, we couldn't see major differences between them, but one thing stood out for the map from HexAuFoil grid, which was less noisy than the other one. And it was the same case when we compared the map with the maps that we have solved in a previous session. And a few conclusions for my short presentation. HexAuFoil are easy to vitrify. We didn't find any empty holes in the hexagons. The HexAuFoil grids are more time consuming when it comes up to setting up a data collection, and this is especially due to image shift calibration that needs to be spot on. But you don't need a lot of good hexagons. One or two are more than enough to get a decent data set, or at least preliminary data on your protein. Particle peaking works as normal, and having gold in the micrographs is not interfering with peaking or downstream processing. And finally, in our case, HexAuFoil improved a little bit the resolution and also the quality of the map, being less noisy. In the end, I want to acknowledge the support from Bond Group, Mwench Group, and also the amazing people from the EM facility from Asbury Center, especially Yehuda and Louis. And thank you everybody for joining us today.
Welcome back, everybody, and thank you for listening to those very good couple of talks. Our speakers will also be turning on their cameras shortly to answer any questions you may have. I do have one question here already that I might as well ask. It says, how does EPU recognize hexagons instead of squares? Is it necessary to have a specific EPU version? Now I can answer that actually myself, but I think it might be useful coming from Yehuda and Sebastian, who've used EPU in earnest.
Yeah, so Thermo Fisher, a few versions ago of EPU, decided to acknowledge the existence of HexAuFoil grids, hexagon grids in general. So when you make up your session, the first thing you have the session setup, you have choose the type of grid you want. I'm just reading it from the EPU screen. You go holy foil, holy carbon, lacy carbon, and holy gold. And if you pick the holy gold, it asks you which geometry you want to use, and then it says square, hexagon, or unknown. So if you're using a weird grid you're making at home, it also lets you do this and not just squares and hexagons. And this applies different parameters inside of EPU to find the hex instead of squares.
Right, brilliant. Thank you very much. Yes, in summary, yeah, and in fact, I know that Thermo Fisher and EPU are continuing to develop their support for HexAuFoil as these become more common in the market. So do please keep an eye out because things are changing. We had a webinar in June in which we had Julio Ortez from Thermo Fisher, who talked quite a lot about what's available currently, and also what will be available in the future. So do look that up if you'd like. There are some further details also online about that we can share. Okay, we've got a few more questions coming in now. I'm just going to ask them in order because I haven't really had a chance yet to process what they're saying. First one, for those of us with two condenser systems, do you recommend using EPU and just having it skip holes in the hexafoils? We use the 0.61 ultrafoils now, but it seems that Quantifoil is not producing them anymore to push us towards using the hexafoils. I'm going to answer the question about 0.61 ultrafoils in a moment, but I'll let Yehuda and Sebastian address the question about skipping holes first.
Yeah. So I would recommend using EPU and skip holes. There are ways to go around with the two-lens system. You can go walk in a different Z height, and then you fool the system to think you do have fringeless. It's a way to do it with. This is how other places sometimes use it, but yeah, the best way to do it is to skip holes. This is the only way that works well. Sorry.
Yeah, I would agree. Yeah, you skip holes, but it's fine. I'd like to emphasize that there are, in fact, 9 million holes on a HexAuFoil. This compares to about 850,000, certainly less than a million on a standard grid. So even though skipping holes is annoying, there is plenty of holes left and still more than on a standard grid. Okay. Even if you allow, perhaps if you skip holes, yeah. So I just want to come back and address the thing about ultrafoils. We are certainly not producing them to push you towards hexafoils. We have had an issue with yield that has meant that we have bought a new piece of equipment that we are currently commissioning. And as soon as commissioning is finished for that piece of equipment, ultrafoil R1.0.61s will be available. And we are very sorry for the long wait, but in the end, this seemed like the best way to be able to get 0.61s to the most people quickly enough. And these grids will be available again end of this year, beginning of next. So it's not, I mean, the only thing I would say is I consider it lucky that we managed to get HexAuFoil up and running just before we were really cornered into deciding to invest in the new equipment for the 0.61s, because it meant that at least we had some form of small hole solution for people in this interim between when the two are available. Okay, I'm going to move on to the next question now. And this one's for Sebastian specifically. They'd like to know if your protein was somewhat difficult to freeze or solve from normal quantifoil drink. Why were you trying HexAuFoil?
Hi. So no, I cannot say that my protein is difficult to freeze or solve it. At least not at this stage, because everything is very well optimized. As I mentioned in the presentation, we are working with a lot of small molecules and a lot of ligands, and we were stuck with the resolution around 2.5 and wanted to push it further, and that's the sole reason that we tried the HexAuFoil, was to see if we can push the resolution. So currently we are still processing some data sets, bigger data sets with HexAuFoil, and we are hoping to get something below 2.2. Would be amazing to start see coordinating water around the pore and so on. So for us as a chemical biology drug discovery orientated group, is very important to get high resolution and try to understand as better as much as possible how our ligands interact with the protein and what changes are happening around the protein when a molecule is bound to it.
Thank you. Could I just ask a kind of follow-up question? You mentioned that the HexAuFoil maps were less noisy. Did that allow you to see anything extra compared to the ultrafoil maps?
At this stage, I'm not entirely sure if I can see something extra. I'm very happy that it's less noisy. So my confidence in, as I mentioned, waters around the molecule is slightly higher than it was before when I'm modeling them in the structure.
Thank you. Okay, we have lots of questions here, so I'd just like to reiterate that we will be getting all of these questions answered and sending out an email to everybody, so you will be able to see the answers to all the questions, even though I don't think we're going to get to everything in this hour. Okay, just a couple of clarification questions here about Yehuda and your tips. You mentioned conditions you use with the glow discharge, that they missed the conditions for plasma cleaning. Could you repeat what you use when you plasma cleaned?
Yeah, so I didn't write the conditions for the plasma cleaning because they are very complicated. In the Tergeo, you have so many parameters you have to change and make sure they're all correct. So I didn't want to go into it because it's a fairly short talk. I didn't want to go into the depth of this. But since we are sending the answers to everyone, I will write exactly what our parameters that we use in our Tergeo, so that you can copy them for yours plasma cleaners. Then it will be easier for everyone to follow exactly what they are, because there are so many parameters. You cannot just say blood force 500 milliamperes or whatever amperes, press a button, that's it. There are so many parameters around it.
Okay, thank you very much. And kind of a follow-up that it says, are you suggesting to re-atlas the HexAuFoil every time the grid comes on and off the stage?
No, I
can
recommend you.
answer.
Yeah,
I would answer this after Yehuda.
Yeah, I recommend re-atlas the HexAuFoils before you're doing your EPU session. So you screen it, it's fine, and then you're happy. And then before you set it up, just re-atlas it to make sure everything is in the right place. Because unlike normal grids, when EPU can correct the image a bit to it, HexAuFoils, because you have so many hexagon and there's so many holes, even as half a hex away, you're gone. You're collecting gold. There's no point in doing it.
Yes,
Okay,
I
thank you.
agree. If the grid gets out of the microscope, re-atlas it. It's worth the time spent to re-atlas than losing the time afterwards trying to process something that's not there.
Okay, thank you. Okay, there's several more questions about blotting questions and things, which we will address in detail when we send out the email.
Yeah.
There are also questions here about that I'm just going to cover very briefly now, so we can do one more interesting one. Questions about using a Leica and questions about using serial EM. And I can tell you that the answer is yes, you can use serial EM, and serial EM latest versions can natively support HexAuFoil. We've had that work done, and you're right about the Leica GP2. You do also need to change the settings to be longer in those as well. I will put the answers when we email, but I can tell you that both of those pieces of information are in the sheet that we send out with every box of HexAuFoil to give you an idea. Okay. So the interesting question I think I'm going to handle here is two things really. One is about concentration of membrane proteins, because I know you guys work with membrane proteins with detergent or nanodiscs. Do we need to use the same kind of concentrations as with standard HexAuFoil?
So my protein is actually a membrane protein, and I use the same concentration as with normal Quantifoil. I didn't see any big differences in between. I think I could have gone with a slightly higher concentration based on the particle number per micrographs that I had, but I think you can use the same concentration. One thing that I noticed, I'm not sure if it's so, because this was a sample with a small molecule, I cannot say for sure, but in this case I could see less aggregated protein than with normal grid, but this could also be because of the small molecule that I used in this data collection.
Thank you. And the last one is, do we have any thoughts? And I think this is interesting enough. I think it's worth going over the hour, but this will be the last question, I'm afraid. Anything else we haven't addressed, we will get back to you in an email. Do we think HexAuFoil has anything that it can offer for air-water interface effects? I knew it would be a tricky question. That's why I was saving it till last.
Yeah.
It's very difficult. I personally didn't look at the air-water interface. I think that the fact that the ice thickness in the hole is very uniform, it could be that it will help compare with the normal grids, where sometimes you are getting a gradient, where in the middle of the hole you have thinner ice compared with the side, with the edge of the hole. But to be honest, I cannot say for sure how it can help, and how it will help or will not help with that. Sorry guys for that.
Yeah, so like Sebastian said, I think because it's a fairly small hole and we can see the hole is uniform in ice, I think it's just if your particle sits in properly inside the ice, it will help. But if they're too big and they go outside, it will not help. So this is why we keep recommending for HexAuFoil use smaller proteins, and this will help anything. There are more things we can test. There are experiments that people are doing to test the air-water interface that maybe we can try to do here, but it takes time and money. But we'll get there.
Thank you very much. And yeah, it is a little early to say anything about the air-water interface, other than the fact that the ice does tend to be very thin, about 35 nanometers, when you blot hard enough. So yeah, so these upgrades, I should emphasize, are aimed more at high throughput and high resolution than they are at addressing that specific issue. Thank you both very much, and thank you everybody for listening today. We have just gone past the hour, so I think it is time to wrap it up. Delighted to have so many of you on the call today, and yes, see you again at the next HexAuFoil webinar. Thank you very much, and goodbye.
Bye-bye.
Bye.